Good morning and welcome. This will be a short course on mathematical modeling of infectious diseases. So this is primarily obviously for my students who take this course in a summer session. So basically this is a course which is taught typically in a month or so, end of May and June at my university. But with the videos, the course basically is based on lecture notes primarily and video lectures. The videos, I should not call them lectures, more like illustrating examples via the videos, video presentations. So for the general audience, I'll try to make these videos more or less self-contained. They will not be 100% self-contained, but because again, the course requires actually quite a lot of reading, and there's a lot of reading material that the students have access to, and they have to read before actually going through the video lectures. However, with some general understanding of the language that we speak here and some of the math involved, which is actually not that advanced or that not difficult, I would say. This should be understandable. I mean, it should be easy to follow for someone who doesn't have access to the notes. Maybe later on, we'll see how this goes. Maybe later on, I will add some links to some of the notes or books that need to be read for better understanding as you go through the material. Because the prerequisites of this class are actually very basic, just calculus 1 and 2, the goal of the course is not too ambitious in my opinion, although I think it's perfectly appropriate for a compact 1 month worth of material. So obviously the syllabus will indicate more, will have more details about the course contents and the goals of the course, but in short, we have basically one main goal for this class. How do we build and analyze an epidemic model? I would say with a decent dose of realism. So let's add here a model which is realistic as possible. Now you will see that this is actually a it's a big word, this word realistic. All I'm saying is that the goal of the course is basically to go beyond just a very basic single equation, which is not that realistic. We're going to start with simple basic equations, but the main goal of the class is to be able to build a model that is reasonably appropriate for an epidemic condition. So it's a population model. The ingredients are differential equations, ordinary differential equation systems. But the meaning of the terms of the parameters will be related eventually to an epidemic model. So the course actually builds up, adds on top of the difficulty. That's why it will start with simple things, and then we will build more and more complex things as we move along, which is the reason that the students who take this class in the summer should expect that the material will be slightly harder in the second half of the course, which is the reason why you should allocate enough time when you go through this material, because there's flexibility on how you go over the material. So try to go a little bit faster in the beginning so you can have enough time on the second part of the class. So not only to build the model, but also to analyze those models in terms of conditions and parameters for disease clearance or persistence. There's lots of questions you can address once you build a model, but at the very least, pretty much any math biology paper that deals with models like this, at the very least, they will want to figure out conditions on the parameters. Those parameters will mean something in real life, obviously, like infection rate, vaccination, death rates, recovery, and so on and so forth. They will put conditions on these parameters for various outcomes. So they will ask under what conditions will the disease disappear in the population, whether it will persist. So it's essentially trying to predict the future to an extent. And for that reason, obviously, the expectation shouldn't be too high. For the most part, the models will give you just an insight. They're not expected to basically have engineering level of accuracy. We'll talk about that more on this later, obviously, in the context of current events with the coronavirus pandemic. The stuff that I'm going to teach doesn't have really that nice of a reputation. I just want to emphasize that this is essentially theoretical math for the most part, and all we do is learn how to basically use equations in the context of biological processes, like in this case, an epidemic. And by the way, the techniques we're going to learn don't they don't rely. I mean, they don't apply just to epidemic models, because the math doesn't care the meaning of the parameters. You can essentially use the same math in a completely different context, in which, for example, you may want to figure out a demographic model, or maybe a cell model in which the individual, I mean, the parameters signify cell level processes inside the body, for instance. Some stuff about the prerequisites. So we have calculus 1 and 2. So purposely this course is made to not assume any knowledge of differential equations. Now, differential equations, those of you who actually took the course will find the stuff in the beginning a little bit easier. But I should point out that even those who took differential equations will find the material pretty new, because most of the techniques we learn in this class are actually not emphasized that much in the course of differential equations. For example, we're not going to solve differential equations that often, because most of the models cannot be solved explicitly. And so we're going to learn techniques in figuring out properties of solutions without actually solving these equations, which is the reason why you can actually approach this class just by knowing, by going over calculus 1 and 2. So anything related to differential equations will be taught along the way. Whatever I need on the spot, it will be taught. And basically you'll have a piecemeal course of differential equations blended in with this modeling course. And I suppose one of the most important prerequisite is the willingness to understand the meaning of math. I should point out that if you have an apprehension for word problems, this course will be more difficult. And to make it easier, you should really make peace with the concept of word problems. For students don't, not all of students obviously, but many students have a problem with word problems, not because they are difficult. The math, in fact, you will see it's often easier. In fact, it's really, really easy. You'll see in the beginning of the class, most of the math is pretty straightforward. I mean, it's just manipulating one type of equation in different contexts. But the wording in the problem forces the student basically to make a connection between the math and the meaning of the math in that real world problem. So you have to make an effort to force your mind to make always connection in your mind between words like, for instance, infection rate, birth rate, many other recovery rate, and so on. You have to make connections with certain variables in the model. For example, later on, we will ask questions like, under what conditions the disease goes away. Okay, so you ask this question based on the model. You have to make the connection that somehow in the model there might be a variable called I, maybe I of t, a function of time t, denoted infected people, and essentially to ask whether the disease goes away or not, it's me asking under what conditions this function goes to 0. So basically, from the wording disease goes away, you have to make the connection in your mind that what I'm asking is under what conditions a limit of a function is equal to 0 as t goes to infinity. So this is the kind of stuff you have to deal with in this class. And obviously it's not going to come automatically from the beginning, and which is the reason why you have to practice and maybe read some of the notes more than once until you get into this mindset. Most of the frustration in the course goes on this aspect. I mean, students will read a word problem. Most of the stuff is biologically related. Okay, I describe a disease, a process, and then a question, tell me how much the infection rate should be or the vaccination should be, for instance, for disease clearance. And then you have to break down that text into pieces and actually put them into variables and functions, and then ask a math questions, basically. So I wouldn't call the course hard, except that this part, if you didn't do it before, will come a little bit harder in the beginning. So a couple of things before we move on to the first part, the first lecture notes, or lecture video, let's say, with some examples related to the notes. In terms of the progression in the course, what we're going to do in the first part, we will deal with most of the stuff we can do using single ordinary differential equations, starting with very simple ones, like the exponential equations, which we'll talk about in the beginning. So most of the we could do quite a lot. In fact, many models, of course, are not that realistic, because to make it single ODE, to make a model in terms of single differential equations, you have to make some simplifying assumptions. We always do simplifying assumptions, obviously, but we could learn lots of the basic stuff just based on single ordinary differential equations. And then in the second part, we will deal with 2x2 systems of ODEs. Either that, or systems that can be reduced via some techniques to 2x2 systems. And these will be slightly more, a lot more realistic, because it will allow you to actually include more than one type of individual in the equation. So you have a more realistic model. So single ODEs, system of ODEs, and essentially anything we can do with them in terms of modeling, in particular modeling in the context of an infectious disease. So with that in mind, the first video that I'm going to post on this playlist will deal with some basic introduction of what a differential equation is, just enough for what we need. We're not going to go too deeply into the theory. And then after that, some examples also related to the homework assigned, which deal with how we analyze properties of solutions in the context of models without actually solving that equation. So with that in mind, I hope you'll have fun, and we'll move on with our first lecture note.